Hello! For our work of cloud computing, we chose to read about Spark partitioning. Spark is a general-purpose cluster framework. Due to its ability to exploit main memory usage, it is able to reduce significantly the latency of the application, covering one of the main problems of previous parallel approaches like MapReduce. Since it's a cluster framework, Spark applications have their data distributed through several nodes. The number of nodes used is closely related to the degree of parallelism. In fact, to simplify, we will consider the degree of parallelism equal to the degree of partitioning. The number of nodes used for the data may be defined by the user or by Spark. In the work of Gonadis et al., they noticed that the Spark not always chooses the best degree of partitioning, which leads to time or resource waste. They proposed two formal algorithms to dynamically define a degree of partitioning, taking into account both metrics. Before presenting the algorithms, it is important to understand how a Spark application works. It is composed of transformations and actions. The first is the application of functions in each resilient distributed dataset, while the second is the trigger of those transformations. It is also responsible of returning the result to the application driver. Note that each action unleashes a Spark job. Another important component is the scheduler, who creates the physical plan for the job from the transformations graph. Finally, an important operation is the repartitioning of data, called data shuffling. This may occur with some types of transformations and results in a new RDD with data partitioned in a different fashion. This is one of the most expensive operations performed in Spark. Suppose we have an application with k transformations. Each set of those transformations that can be executed without data movement in parallel and overall data partitions is called a stage. When we instantiate it over a data partition, we call it a task, and it represents a unit of the physical plan. The author started by presenting formulas for the execution time in function of the number of machines used. The first formula translates the behavior of a simple application that doesn't change the degree of partitioning during RDD manipulation, and also of applications that do change it, but only during computation. The second translates the execution time of applications with data repartitioning. The difference is that in the last formula, it is necessary to separate the behavior of sender and receiver nodes. Now consider the directed acyclic graph G for the execution plan, where each vertex represents a set of stages executed with the same partition degree. The goal is then to find the optimal partition degree for each vertex that minimizes the resource consumption and maintains the execution time lower than the execution time for the initial degree. The algorithms developed worked on top of the dependency graph of G. There are two main approaches. The first is a greedy one that calculates the benefit of each vertex I for all partition degrees J and selects the best combination. GLocal calculates the benefit as the difference between running times for vertices I that are partitioned in J partitions. Gxt applies GLocal recursively to all the descendants of I in the dependency graph. And gfull enforces all vertices in a path of I to a vertex without outgoing vertices to have degree J. The second approach applies the iterated local search in the graph by iterative and randomly perturbing the current solution in search of a local minima. The authors conducted experiments with a real-world dataset called AudioSlobber. In order to perform data mining tasks, they elaborated a collaborative filtering model to give user recommendations, cluster data, and created a model to find frequent item sets. They also generated different applications with different deck sizes and types to test a wide range of applications and improve the solution's reliability. Each application was executed 100 times for different values of epsilon. It was possible to conclude that the solutions worked very well on the real-world dataset, reducing the running time in 20% and the resource consumption in 50%. G-Full was the overall best solution. Also, it was possible to observe that epsilon and running time are highly correlated in the greedy algorithms. Although ILS was not the best solution, it revealed interesting trade-offs between resource consumption and running time. The deck size revealed to have little influence over the optimization. These solutions rely on the formulas presented earlier, and for that, some parameters need to be estimated. This, however, it is not an easy task and doesn't have an expensive solution yet.
Titian, data provenance support in Spark. Debugging data processing logic in Spark is a hard and time-consuming process. Today, some of the more practiced patterns are trial and error debugging, where the developers replay a portion of the data processing logic on the data, dividing the tests by operations. Identifying the subset of the data that led to the error, dividing the tests by data. This problem indicates the need for capturing data provenance for Spark, which is the ability to see the data's origins, what happens to it, and where it moves over time. Previous approaches exist that try to tackle this same problem, all with their own limitations, such as use of external storage for the lineage information, limiting their scalability. The queries are only supported in a separate programming interface, or it's provided little support to view intermediate data, or replay data processing steps on the intermediate data or some alternative data. Titian uses several kinds of agents to introspect the Spark's stage DAG to capture data lineage. The paper discusses 6 kinds of agents, but their common responsibilities are to generate unique identifiers for each new record, associate output records of a given operation with relevant input records. When the main program encounters an action, due to lazy evaluation, Spark translates the series of transformations, leading to the action into a DAG of stages. Titian hijacks this step and adds to the graph capture agents before it is submitted to the task scheduler for execution. This integration into Spark's partitioning contributes greatly to its computation results. Titian stores all data lineage information in the block manager, which is Spark's internal storage layer for intermediate data. The associations done by the agents are stored on a local block manager table. Titian agents batch associations in a local buffer that is flushed to the block manager at the end of the operation. To decrease the cost of data exportation, Titian flushes intermediate buffers asynchronously, reducing its impact on performance. The lineage information is then compacted into a format exploiting optimized data structures, like routing bitmaps. Experiments were made using free versions of Titian and 2 previous solutions to bringing data provenance to Spark, named RAMP and Newt. The free Titian versions are Titian-D, which stores the data lineage distributed in the block manager local to the capture agent, Titian-P, where all agents, other than the last, propagate data lineage downstream. The final agent stores on the local Spark block manager the complete lineage of each individual data record as a nested list. And finally, Titian-C, whose agents write the lineage data to a central server. The experiments evaluate the overhead of capturing data lineage in a Spark program. For these, it was generated a couple of datasets, with sizes ranging from 500 megabytes to 500 gigabytes. On these datasets were defined 2 simple Spark jobs, grep for a given term and a word count. Frustrations found by using previous solutions of data provenance have sparked the development of Titian, which, by extending the Spark RDD abstraction, makes use of an environment familiar to the Spark programmer, providing data provenance in a more accessible way. Titian opens the door to some interesting use cases, such as program debugging, data cleaning, and exploratory data analysis. It also proved to be faster and more scalable than previous solutions like Newt and Ramp.
In the last studied paper, it is exploited the possibility of using a Spark implementation for the dbScan machine learning algorithm. In the machine learning domain, dbScan is a well-known clustering algorithm based on density. Its greater advantage is its ability to identify nonlinear clusters and to recognize noisy data. Using an optimized parallelization strategy for these algorithms turned vital in order to maintain scalability with the growth of the quantity of available data. Parallel dbScan has been implemented in the past. Generally, an MPI implementation suffers from lacking a fault-tolerance strategy and demands programmers to take care of details, such as how to partition the data, synchronization, and how to deal with communication. In addition to that, when using the master-slave model, the communication costs between the master and the slaves are observed to be dominant. This paper tries to propose a new, scalable, distributed, parallel dbScan algorithm implemented in Apache Spark that tries to address these problems. In the master-slave model, the master reads the whole data, transforms the data into the appropriate formats that can be processed by the slaves, and then sends back the data to the slaves. When implementing the algorithm in Spark, the objective is to keep communication costs in a minimal. There is a driver that launches a set of tasks to the executors. In this model, every executor reads data from disk and they only reads their whole part of data, generation partial clusters based on the points they read. When implementing this algorithm, there are two critical techniques which are important to guarantee that the parallel processing is more scalable and efficient: how to partition input data and how to merge partial clusters. When partition input data, in order to guarantee that nearby points are assigned to the same subdomain, the spatial location of the points are used to build a key tree structure. It is basically a multi-dimensional binary tree, and it's used to guarantee that approximately the same number of data points are assigned to each processor. After data has been partitioned, each executor does a traditional dbScan algorithm over the data. Then, the challenge is about merging clusters generated in different executors. This is important because if two clusters share a same bordering point, it means they are actually the same cluster and should be merged. The traditional approach of using these joint set data structures is very expensive. So, a new approach was done by using an HashMap data structure in order to hold the relationship between data points and their neighbors. There are three main benefits of using this. One of them is it turns possible to merge partial clusters without communication with other executors. Other is that the search operation on HashMap takes about O1 to be done. This data structure is also very effective in terms of storage space. The greater objective was to evaluate the effectiveness and efficiency of the parallel dbScan algorithm using the Spark implementation when compared with the state-of-the-art MPI-based approaches. In order to do that, multiple datasets of different sizes were used. For datasets of small size, the variation of speedup with the number of cores is similar between the Spark and the MPI approach. However, even in this case, the Spark implementation achieves better performance. For big datasets, the performance of Spark is significantly better than the MPI approach. In the MPI, the communication costs between master and slaves become dominant, leading to a smaller speedup when increasing the number of available cores. The possibility of identifying nonlinear clusters and to recognize noisy data are the features that granted the popularity to dbScan. Despite that, previous parallel implementation of the algorithm suffered due to the use of the master-slave model and the ineffectiveness of the merging process. The new proposed approach not only uses the Spark to avoid communication costs, but also proposes a new way to merge the partially generated clusters. The lack of communication between executors leads to a better scalability than the state-of-the-art MPI-based approaches, mainly when the quantity of data is big, suggesting that Spark could be a viable approach to use parallel dbScan.